Hey everyone, this is Dr. Walker. In this video, I'd like to go over the example from v577, which is on the right-hand rule number 3, dealing with finding the magnetic field due to a current loop. In order to do this example, you also need to know v576, which is finding the magnetic field due to the current loop, not just the direction. So the first thing to note here is that we have 4 different wires or loops, and they each have the same current. We want to figure out which one has the largest magnetic field strength at point P, which has been labeled in all cases. We're not told which way the current is going, so I have just randomly labeled it to go in a clockwise direction for the loops and to the right for the straight wire. The direction of the current doesn't matter because we're looking for the strength of the magnetic field and not its total direction. The next thing we need to know is how to find the magnetic field due to a loop and due to a straight wire. I've written these two expressions here. For a loop, the magnitude of the field at the center is mu naught I over 2r, where r is a radius. For a straight wire, the magnetic field at a distance little r from the wire is equal to mu naught over 2 pi little r, but I went ahead and substituted big R for little r here because the distance is also capital R. All right, so I don't want you to think that there's going to be a lot of computations for this. You should be able to think about this problem conceptually to figure out where the field is strongest. We already know it's not case number 2 because we know the field at number 1 is bigger than the field at number 2 because number 2 has a pi in the denominator. What I want you to think about, first of all, is what happens to the magnetic field because we have this smaller little inside loop here where the current is going counterclockwise for number 3, but it's going clockwise for number 4. Does that mean that the field at point P is going to add up in each case, or is it going to subtract in each case? So that's definitely going to help you find the answer. And then the other thing is to figure out how can we apply this equation here, B equals mu naught I over 2r, to cases 3 and 4. So think about it and pause the video. Okay, hopefully you've thought about it. So this equation tells us that the smaller the radius, the bigger the field. So we can think of case number 3 here as half of a loop with a current going clockwise, and then half of a smaller loop with a current going counterclockwise. If you use right-hand rule number 3, for the top half of the loop, your fingers are curling clockwise, your thumb should be pointing away from you or towards the page. But then for the little half of the loop here, with the current going counterclockwise, if your fingers are curling counterclockwise, your thumb is pointing towards you or out of the page. So the fields produced by each of these two segments, which I will color in red, the fields produced by each of these two segments are going in opposite directions, so they're going to cancel out. While for number 4 here, we have a field produced out of the page a field produced into the page for both cases because the current is clockwise in both directions. So the fields add up for number 4. So just without doing any calculations, we know that the field at 4 is going to be greater than the field for case number 3 because the fields add up here while they subtract here. And then once again, without doing any calculation, we now need to figure out, well, which field is going to be stronger, 1 or 4. And what we can do is we can consider loop number 4 here to be half of a loop where the radius is the same as loop number 1, but then the other half of the loop has a smaller radius, and we can disregard the straight segments because the straight segments do not produce a magnetic field at the point. Feel free to let me know why in the comments below. But if we consider this as a big half loop and a smaller half loop, And we know that the smaller the loop, the bigger the field. Then that tells us, without doing any calculations, that the field will be stronger at point P for loop 4. So that answers our question. Now, just as a quick aside, let's say you do have a problem where you are trying to calculate the field due to a case, for example, such as loop number 3, then the way that you would do that is you would calculate the field due to the big half here. And since the field due to a complete loop is mu naught over 2r, then let me actually color the top one red. So the field due to the top part here is going to be mu naught I over 4r, right? I have cut this field in two because we only have half of a loop. And then we said the field due to the small loop is going in the opposite direction, coming out of the page. So we're going to subtract, let's make it magenta color here. We're going to subtract a field mu naught I. Now the radius is half, so we have r over 2 instead of r, but we still have a factor of 4 because we still have half of the field due to a complete loop. But what this gives us here is mu naught I over 2r. So we can see, this is how you're going to calculate the field, and I'll leave it at that, but you will just do this value minus this value. While for case number 4, you would do the red value plus the magenta value. And you should be able to see that the case number 4 has the strongest field at the center.